Okay, so right, let me just get everything up and then we can go ahead. Let's do a do it like this. Present from the beginning. Okay. Sorry about this. And oh, sorry. Actually, I'll present this screen and then it'll be a bit easier for me. So. Hello. So can everyone see the slides?
Yeah, it's working.
Yep. Okay, great. So yeah, today we'll be covering convolutional neural networks, CNNs, and they're pretty much the building blocks of kind of modern computer vision. So we'll look at kind of where are CNNs used, or like why should we actually care about them, and we'll look at how do they work in terms of like kind of the actual maths and the intuition of what they do. And then if we have time, we can look at the overview of like some common architectures, and I'll also show like a short demo, I suppose. So first of all, where are CNNs used? So they're used for stuff like a classification of images. So you have an image and then you're like, it has like a dog in it and you want to know, is there a dog or is there a cat, or just yeah, object classification, object detection. So image segmentation, meaning like you separate out, you have kind of like a mask over the image of saying, okay, this part of the image is the cat, etc. And then a few other ones, but yeah, I won't bother listing all of them. So let's kind of take a step back, and I assume if you I think been to the other lectures, then they spoke about neural networks a little bit. So let's take a look at kind of normal fully connected neural networks and why they're kind of quite bad for classifying images or doing kind of computer vision. So pretty much say like this is just like a one hidden layer fully connected neural network. So we have like some inputs, and these inputs, as like a recap, they go into each one of those each one of the nodes of the next layer. Then they kind of concatenate together or like added together and then put through an activation function. So okay, so we have this. So let's say we take this and then we want to classify an image where it's like 200 by 200 like width and height by 3. So that's the kind of the RGB color depth. So that will be 120,000 connections per a single neuron in the hidden layer. So for each hidden layer neuron, we have 200 times 200 times 3 kind of inputs going in. And that's only for one neuron in the hidden layer. And then if you have obviously more neurons, then there'll be more connections. So essentially, we don't really need that many connections, and having so many connections will be very prone to overfitting. So for example, maybe there's like a more efficient way of doing things. Maybe we're often looking for like the same features in different parts of the image. For example, say we're doing like a classification of a cat. And one feature we might want to look out for, I mean, this is done automatically, but let's just add in like an intuitive example. Let's say one feature we might want to look out for is like an ear of a cat. Then, well, that ear could be anywhere in the image. So it could be like top right, bottom left, middle, whatever. So maybe there's a way we could kind of share, like cut down the number of connections and kind of just reuse the, let's say we're looking for the ear of a cat. Then we could possibly just like have one set of connections that classify like, oh, here's like an ear. And we could kind of just scan that over the whole image instead of having for each kind of input kind of feeding into the next layer, if that makes sense. So So dealing with images. So I think, oh, okay, this was supposed, yeah, there you go. The slide. So so for example, let's say we have an image which is 32 by 32 width and height and 3 wide, 3 deep. So here's what we would kind of apply that intuition of, say we would have like a filter. So we see this filter being like a 5 by 5 filter, and this scans over the image and looks essentially for certain features. For example, the ear of a cat. So, and then if it like kind of finds like a feature like that, then its output would be higher here. And if it doesn't find a matching feature, then it'll be lower. So that way we can kind of, so these are the weights, for example, going, so we have the values times multiply the weights and then feed that through an activation function. And then we have the output value here to represent kind of how well is it matching that feature. So now, compared to the feed forward fully connected example, this just minimizes the number of weights looking for a certain feature, for example. Okay, so let's look at kind of what filtering means and what a kernel is, and then we'll kind of build it up to the like convolutional neural networks. So just to get some intuition of how can filters be used. So here, if we're looking for, say, a vertical line, so we have black squares on the outside and just a vertical white line. If we, for example, take this bit and we do a dot product, meaning we take like -1 times -1, for example, here, and 1 times the 1, and then we just kind of do element-wise products, sum them together, and then we divide it by like, we normalize it by the number of, by the size. So here we would get like a perfect score of 1, because -1 times 1 is 1, and then 1 times 1 is 1. There's 9 of them, we divide it by 9, we get 1. So say we're using a stride of 1. Stride, it just means how, like, each step, how much do we move by? So stride of 1 means we just move by 1 square. Now, if we're matching this filter against this, how well does it match a vertical line? That would like this. So now we get a score of a -1/3 if we do the dot product. So, okay. So as you can, if we keep going, then we would get this kind of output. So you have 1, 1, -1/3, -1/3, a third here. So as you can see, they kind of roughly correlate to how well kind of the block we are matching here is matching against the filter we're using. So we have like the perfect score of 1 and 1 in the top left. Hopefully that makes sense. So then we could extend it to multiple filters with depth. So let me actually maybe go on this website so I could pause it. Just give me a second. So this is using the Stanford has a nice visualization of what's happening. So we have here. So what's happening here? So in this case, say at each step we may want to use multiple filters. So that's all it is. It's kind of usually multiple filters instead of just the one. So this is a 7 by 7 by 3. So this is just kind of a volume. And so these are like, yeah, width, height, and depth, for example, like RGB colors. Then we have the filter for, I don't know, it's looking for a certain thing. We don't really care about that too much. This will be kind of learned in the neural network as we train it. But so this would be one filter. And since we're doing a dot product, then the number of like elements, so this is like three deep. So we need to have 3 kind of layers of this filter so that we could do the dot product of element-wise kind of products here. Yeah. Okay, so for example, yeah, we do the product here. So we're using a 3 by 3 filter, and the depth has to match. So always in convolutional neural networks, the depth has to match, because you could choose the width and the height of your filter. This is 3 by 3, and that's just the window that you're sliding over. but the depth has to match the depth of the input, just because of the way we do the dot product. Okay, so we do this and we get, for example, a value of 2. Yeah, so we have 2 filters, meaning the output volume would be too deep. So each kind of image here, each layer was corresponding to the filter. So this filter sliding over at this part will give us a 2, and if it slides over, for example, here, it will give us a 4, etc., etc. And then if you, I think this will move on to the next example, and then the other filter slides over the input, and we generate the other output. So hopefully that roughly makes sense of kind of scanning for features, essentially. There we go. So each filter is just looking for a feature, and then we have multiple, for example, for a certain input. I don't want to do this. Yeah, there we go. So we have multiple filters, so they're just like, given the input, we're scanning for a bunch of things, and then we have an output volume. Okay, so this is what a convolutional layer is. We already, yeah, so just going back to the slide we already had. So here we would be a 5 by 5 width and height filter. And we just slide it over, generating, as we've seen in the kind of visualization on the website. Okay, so yeah, hopefully that makes sense. We'll look at, so the dimensions change. So the input was 32 by 32 by 3. After applying the filter, we have 28 by 28. And now the depth is 1, because this is just kind of for, say, 1 filter. This reduces because we'll look at into the maths of exactly the dimension kind of reduction. Yeah. So yeah, we have multiple filters. Then the depth would be, the depth of the output will be the number of filters we use, because each filter kind of makes a layer of this. After we have the outputs, we usually apply like an activation function on them, so like a ReLU function. Okay. So let's kind of talk about kind of how, for example, for classification, how would a CNN work? So we have an input of a dog. So at each layer like this, so we have like the convolutional layer and then an activation function. So these are looking for just features. So for the low-level features, it will be kind of closer to the actual input. So here it could be looking for, say, like vertical lines, as we saw before, or stuff like that. Then the mid-level features have an input of those previous features, so they're a bit more abstract. And then as you go higher and higher, then we get like a higher level representation of what the actual image is. And then once we condense down the big image, so this could be like however many pixels wide and tall and free depth, we reduce it down to a smaller kind of representation. So we just have like a yeah, just like a representation, for example, like this. This is just like it doesn't make much sense looking at the images, at least for me, but this is kind of what the neural network is learning. And then at the end, we want to classify it like, oh, is this a dog or is this some other animal? So we take this high level representation and we put it through like a linear classifier. So here would be kind of like a fully connected network at the end. And the reason we do this is because the dimensions of this image are a lot higher than like the dimensions of here. So here we have like a lot less data points to actually work with, because it just kind of takes the abstract. Okay, there's like roughly a dog and it's roughly here type of kind of abstract representation, rather than like the individual pixels. And then if we have like a more abstract, more condensed version, we can classify it a lot easier. So that's the intuition behind it. So let's look at, for example, the dimensionality of what happens when you have a filter. So say we have an input of n by n, and then we have a filter size of like f. So as we slide it over, I mean, this is just a formula if you want to like reference it later or just know what's going on. So as we slide it over, how many kind of outputs are we going to get? So this will be one output. Then from here will be another one, and then we will have another one. So we can fit in 3 of those kind of blocks. We can slide it 3 times. So that's why we have an output of 3. And the same again is it's n by n, so the same would apply 3 down here. But overall, the formula is we have n take away f, so n, those dimensions, divided by the stride plus 1 is then like the output dimension. So the stride, as I said before, is how many do we go by. So if we, for example, did a stride of 2, then there will be 1 block here. Then we stride it by 2, and there will be another one here. So it will be an output of like 2 by 2 in that case. And when you're specifying the neural networks in code, as we will look at later, you can specify like your stride, and the x and the y stride could be different. Usually they're the same, but they could be different if you want to. And also the width and height of the filter, you could vary that accordingly. That's just kind of going through. Oh, yeah. So this should be labeled. So stride 1, stride 2. We have like an output of 2, as I said before. Then I think stride 3 is it wouldn't work because like you couldn't stride by 3, it just wouldn't fit. That makes sense because yeah, you can't actually fit it. So you could see if it would actually fit by looking at the maths. Sometimes we want to preserve the dimensions of the image. So as you can see, if from the input to the output, from the input to the output, the dimension reduces. So we have like a 5 by 5, and we get like a 3 by 3. But sometimes we want to preserve the output size. So what could we do in this case? We could do padding. So you can adjust the padding accordingly. So you can just like put a border around it. And this, for example, if we have a stride of 1, as in the previous example, we have a 3 by 3 filter. Now the input n length is n, is 7. So when we apply the formula, it will be we get an output of 5. So we don't really care about the values here. It's just kind of to preserve the dimensions of the original image. Here's just a slide of the same formulas we are looking at, but it's a bit more general. So like if we apply padding, so say we have number of filters, so that would be our depth. So the output depth is the number of filters as we saw before. The size of the filter is f, but again, like if you do it on like separate sizes for each dimension, then the formulas will apply for that dimension. Yeah, so then unstride S and padding P. So this takes into account kind of the padding. So essentially it's the size of the original input plus padding. Say we have a padding of 1, then we have to do 2 times padding because it's on both sides. So that, and it's just applying the formula from what we had before. So this is just to preserve the original dimensions of the image. Okay, so there's another kind of layer that we could do. It's called a max pooling. So this is used commonly with kind of in CNN architectures. So essentially what it means is, say we have this as an input, and we want to kind of condense it down. Like I'll show like an interactive example just a bit later on, but we want to condense this down to kind of get this representation of, okay, roughly what's in like top left, what's in top right, bottom left, bottom right. So what happens here is, so our max pooling of, for example, 3 by 3 max pooling with a stride of 2, then that means we'll slide over the window, but instead of doing a convolution as we did before, so instead of doing that dot product, we just take the highest value. Well, yeah, we take the highest value, and what was the actual formula here? Yeah. So essentially, yeah, we take the highest value and we average them out. So for example, we get 1 here. And again, if we apply another max pooling layer, we'll have like summarizing that area to being 1. So roughly, if you see like on this side, we have kind of high values. On this side, we have lower values. And that's kind of, we get like a more dense representation of that. So we're losing a bit of information, but sometimes that's a good thing. We don't want to deal with that much information. We just want to kind of summarize it. So this is max pooling is just summarizing an area. It's doing the sliding window thing again, but it's just within that window, it's just summarizing what's kind of going on. So here's like an example of a CNN architecture for classification. So say you have your input image, you do the sliding window with however many filters, and then you get this as an output. Then you can pool this, so you apply, say, max pooling, and that becomes like you reduce the dimensions because you don't want the dimensions to kind of be big. Ideally, you want to kind of condense it down to be the smallest representation as possible, but still kind of being accurate. So yeah, so you apply pooling, and then we could apply another set of filters on that. So we apply a filter, it's filter plus an activation function for each kind of value, and then we can pool again. And now we have like a this is the kind of the high level representation set that I was talking about earlier. And we can, now that we have from the original image, we have a higher kind of representation. So we could just feed it into like a fully connected classifier and just classify on those features. So if we look at, for example, like an interactive, just give me a second, the website is loading up. Just one sec. I think PowerPoint's crashing on me. I don't know why. Oops. Okay, let me maybe restart it. Just give me a second. I apologize for this. Okay. Slideshow. Beginning. Okay, can we see the PowerPoint again? Let's just skip through where we were. I don't know why it crashed on me trying to open the link, but there we go. This is the website I want to go on, and hopefully we can just kind of go on the website now. Oh my god. All right, I'm just gonna copy and paste the link because why is PowerPoint? I'm really sorry. Yes. Great. All right. But this time I'll just copy and paste the link so we don't have to go through this again. Anyway, so this is what I wanted to. Maybe the website is down. I think, if anything, we can just kind of skip this example, but I wanted to show you this website. It's has a very nice visualization of what's going on. But yeah, I guess the website is just down, so that's a shame. All right. Okay, let's go back. What the website was kind of just an interactive way of talking about what I was talking about earlier. So here, for example, you can draw a character. This is like a character classifier. And then it shows you, so after like a convolutional, you can see the outputs of each after each filter was applied. So as you can see, for example, here, so this filter applied like on this image. So it was looking, I guess, for kind of roughly horizontal or like slightly diagonal lines. So like we get a higher value where there's kind of lines like that, and lower value where there isn't. So that's, again, as we were saying, the filter matches stuff it's looking for. And you can see this one's kind of looking for vertical lines, for example. So that was just so that, and then from here to here, there was like a pooling layer applied. So as you can see, the pooling layer just summarizes roughly what's in this image. So it just takes away kind of useless noise, I suppose. For example, this image and this image, they're very similar, and you're not losing that much information. You're just summarizing it, and you don't want the dimensions and number of inputs and outputs to kind of blow up too much. So, okay. Again, then we get a bit more high level. So these are kind of a bit harder to understand. Like, so we apply another convolutional layer on top of these. So the depth of this is how many outputs we get. And yeah, so I mean, there's not much we can say about them. It's just like we do some reasoning based upon this as an input, and we get this as an output, and then we can do the max pooling again. So now we have like a higher representation of the image. We could put it through a fully connected classifier. So this is 2 layers of just them being fully connected, and then we finally have the output of it's a character classifier. So we have from 0 to 9, and the one that lights up like the brightest, then that's kind of what it thinks is the output after it's been trained. Does this make rough sense, by the way? Any questions on kind of the intuition or what's kind of going on behind the scenes? Okay. Just give me a sec. Okay. All right. In that case, then I guess we could just look at how we're doing with time. It's not too bad. Okay. So we could look at some common architectures. For example, this is one of like the early, like most successful CNN architectures. And as you can see, compared to this example, it's a bit deeper. So usually, the deeper your models are, the better, because you're kind of at the end, you're working with like higher abstraction of your input. So it should be a lot easier to separate it in the classification stage. So again, so we have the input. Let's just walk through it real quickly. So we just have a 3x3 convolutional layer with 64 filters. We apply that, for example, twice. Then we can pool it to produce the dimensions. We can apply more filters, pool it again, and etc. And then again, so this is just a common classification thing. So we have the pooling, and then a few fully connected layers, and then we actually use that for predictions. Another architecture that was quite common, was like very influential, was the ResNet. So as I said before, it helps with if your models are deeper, usually you're kind of working with higher abstraction of your inputs, and therefore it's a bit easier to classify at the end or do whatever. So yeah, by that logic, we would want to make it deeper. However, for example, if we compare this to this, the problem with having a super deep, or if we made this, let's say, even deeper as a network, then we get what's called like a diminishing gradient, so like gradient vanishing problem. And that means essentially so we classify it and we give it the output in training, and then we compare what is our predicted output with what was the like correct output. And so we have like a labeled set, and we compare our predictions with their true labels. So in that case, we would get like an error, and then we feed that error through each kind of nodes and connections, and we will change the connections with backpropagation. Hopefully this was covered in the previous lecture, but Backpropagation literally just kind of goes through the network and adjusts each weight in order to minimize the error. So it spreads out the kind of the error between all the weights and adjusts them accordingly, like in proportion of how influential they were. So as you can imagine, if you go deeper, then this spreading out of the gradient, which is based upon the error, this spreading out kind of by the end, if you try to go back to your inputs, then you'll get very small values for the actual like relative errors on each connection at the, when you're very deep into the network. So that's quite a bad thing, because then we can't make much learning progress and we can't adjust the weights as much at the beginning as we could at the front. So this ResNet architecture was kind of attempting to solve that problem. So what it was doing was having kind of what's called the residual blocks. Say we have an input X going in. As normally, you would kind of apply like a convolutional layer, an activation function, convolutional layer, etc. But the key thing that they did was feed the input through and do element-wise, I think, addition on it. So essentially, what this is learning is the residual kind of difference. So if you look at it, so this is addition. So if this was 0, the output of this was just 0 elements, then we would get X out. So, but usually we would want that to be some kind of processing going on. So this is just learning the residual weight. So like, how should it change the input for it to be kind of a better representation, or for it to do the task better. So yeah, we have two things from this. So the one big thing, as I was saying, is kind of solving the problem of the vanishing gradient stuff. Is because we have this connection that's kind of unaltered and it doesn't have any weights. And the kind of gradient information the error information can flow through the network quite easily. And so you can get to the kind of deep into the network while still preserving kind of the relative errors of those connections there. So it helps it learn. And the other thing is it's kind of for example, in the case CNNs could be used for stuff like noise reduction. So you have a noisy image and you apply your network on it, and you want like a clean image, so kind of denoising. In a denoising example, you want your output to be kind of very similar to your input, just like with the noise removed. So this is where like a residual network could be quite good, is essentially the output is we already have X being added here. So all the network has to learn is essentially the inverse of the noise. Like it has to just learn to cancel out the noise. And because it's addition, so if this input has some noise, this cancels out the noise. And if you add them together, you should get like a cleaner image. Hopefully that makes a bit more sense. And okay, so if you compare the previous two examples, so VGG compared with ResNet, you can see that the ResNet is a lot deeper. It has a lot more connections, but it doesn't struggle from that problem. Doesn't struggle from that problem of the vanishing gradient. Okay, so any questions on? So this is, I think, the end of the slides. Any questions roughly on what was covered here? Okay, guess no questions. So what we could do is we could run for a quick example of how would we actually code it up in a framework, or like say PyTorch. Find my example. So just a second. Okay. So here's a notebook which is on the repo that I linked. We can do a quick run through of the repo and kind of how would we actually create the neural networking code. So let me restart the kernel. Okay. So let's restart it. Okay, so first of all, we have some imports. So we'll be using PyTorch for this example. So we just import standard PyTorch libraries. And then, okay, so if we're like training on stuff, then we actually want to have some hyperparameters, for example. So for example, the batch size, this is how many images kind of at once you push through the network. So it could be very inefficient if you just push like one image at a time through the network. So if you could batch them together and do it like in separate batches, then this could use your hardware a little bit more efficiently. So in general, you want to use like the higher batch, the better, like as much as you could fit in on your GPU or whatever, because you could run out of memory if you try fitting in too much. So you have some hyperparameters. This here, for example, is we're choosing a device we could be working with. So if you have a GPU, for example, as I do, so I'm just, let's say, running on the GPU, and the device was set to torch the device CUDA 0. So this is the first GPU, NVIDIA GPU that I have. Okay, then we want to get the data. So here I just defined some transformation kind of layers. So we have the training set and the testing set. We're doing this classification on the CIFAR10 dataset. So if I could just show you what the CIFAR10 data set is. And data set is we have images like this. They're very small images, and then it's just used for classification. So we have a bunch of images for airplanes, dogs, stuff like that. So that's what we're training this on. Okay. So we make this is just standard PyTorch stuff. We make a data loader based upon the data set. So this is just feeding in the CIFAR data set, and then this makes it so we could use it in training as a nice data loader. We could apply stuff like shuffling and number of workers. So this is like multi-core stuff where we could split up the work between different cores. Then we define our classes. So the classes for that was, as we looked, it was like, for example, plane, car, bird, cat, etc. So we're just working with these classes. Let's give a quick example of, do I have no train load? I didn't run this block. Okay. Let's just run this real quick, and then we could actually see what we're working with. So I have a function with image show, and just takes an example from the data loader, and we'll plot it out to see what it does. Well, what the input image would be. Okay, so yeah, they're very low resolution images, but as we can clearly see, it's a deer. So this is like 32 by 32, I think. Yeah, 32 by 32, and a depth of 3 because we have three colors: red, blue, and green. So yeah, so this is the type of stuff we're feeding into the network as an input. Okay. So here we could actually build up the network. So we do it as a class. So we define a class. This would be like, we could call it whatever we want, but let's call it a net. So for our network. So then first of all, we initialize the blocks, what we're going to use, and then we define kind of how are they connected together, if that makes sense. So say we're going to have a convolutional layer, conv1d, or just conv1 as a make a convolutional layer. So this is as we were saying before. So we have, for example, the output channels being 6, as you can see, and that corresponds to how many filters do we have. And then the kernel size, again, this is like a 5, so this will be a 5 by 5 filter on 6 of them. Max pooling again, so max pooling, we have the kernel size because it's like a sliding window, and then the stride. If we wanted to, we could like look up the documentation of conv2d, and convolutional layers conv2d, for example. here we could specify more parameters. So we could say, yeah, the kernel size, say we want a different on the X and on the Y axis, or stride, we want a different here. We could also apply padding and some other options that we get, but we won't go too much into them. So yeah, so we define our layers that we're going to be using and some fully connected layers. And then we define the forward function of, okay, how are they connected? So we have the input being the 32 by 32 by 3 image. We apply conv1 to it. Then we apply a value activation function and then the pooling. So this is very similar to the diagrams I've been showing. We did a similar thing with a different convolutional node, conv2. Okay, this x.view, this just changes the shapes. So because the output of the convolutional layers, as we were saying, or even the max pooling, is a volume. So width by height by depth, essentially. But a fully connected requires kind of like a vector input. So here we're just flattening it out. I think I accidentally pasted. I think I accidentally pasted pool there. Yeah, okay. So okay, so we're just flattening it out from the volume to be a vector. Then we apply a fully connected layer on that activation function, another fully connected layer activation function, then the final fully connected layer, and then we just return X. So this will be kind of our classification stuff that we use. There was a library called torch summary, so I just imported it here. Torch summary import, and we could kind of display what is the network actually looking like. So it just gives us kind of what are the output shapes and of each layer, and it gives us some statistics about like the total number of parameters in this whole network is 62,000, which is quite like low, and like how much memory does it take up. Okay, and okay, so this later part would be going into kind of transfer learning, which is using like a ready-made kind of pre-trained network and just adapting it to our classification problem or whatever problem you're having. So instead of using a small network and trying to train all of this, maybe it will be helpful if we have a big network already trained on a different data set. So ImageNet, for example, and we want to apply it on our data set. So we could do it. So here, for example, I'm just importing the ResNet 18, which is, we will look at ResNets, what they are. So this is just a variation of the ResNet network. Okay, here we would be setting that we just want to extract the features from it. So we set that requires grad to be false. That means when it's like learning, because we will be kind of taking the network, we're freezing it here, so it doesn't change during training, but we're adding we're changing kind of the stuff at the very last part. So you can see the network, and this is like a linear classification layer, for example, and has 1,000 categories. So here we could just be changing this part to adapt it to our, I think we have 10 categories in our example. So this is if I for example print num ftrs, so it's taking in I think was it 512. Yeah, so the resnet.fc, which is the fully connected layer. What could we find the fc? So I think the torch summary doesn't give you the actual names, but we have them here. So fc1, fc2, fc3. We could kind of use that. If it was our example, but I guess ResNet, so this layer would correspond to the fc of the last one. So it's taking in 512, as we can see, and then we'll just replace it with our layer. So instead of having kind of going in 512 to 1000 categories, we could change it so it's we have the input 512, but instead of it goes to the length of classes, so this the length of our categories, which is I think 10 in our example, and then we send it to device, so we send this to the GPU. Then we could actually, I think, do torch summary on that. So let's do torch summary on this instead of printing it. And as you can see, at the end, we've changed it, so it's a linear classification of 10. So as we did before, all of this will be frozen. So this is just a feature extraction. So as we were saying, going from low-level features to high-level features. And then we just change it. So this is frozen, so this won't change when we're training. And we're just kind of training, we're replacing the head of it, and we're just training the classification part from those kind of high-level features. So we have 10 classes, and we do that. I'm just printing the ResNet here. We could define, okay, so you have train, and we could train the network. And then here it's just kind of, it'll be training, and then at the end, we could save the network however we would want. But yeah, anyway, and then the rest is kind of testing of like, oh, how well are we doing in terms of how well are we predicting the classes in this example. But this just runs through basic transfer learning and also creating our own networks. So as you can see here, we've created our own network, and then we could also try transfer learning. So instead of train, we could do train, for example. So we could either train the ResNet, so we have a train net, and so we finish training, for example, and we have a loss. It's not really going down right now. Or we could like train the ResNet 18. Okay, so I think this will mainly conclude the lecture. Are there any questions with regards to what we spoke about? Okay. Okay. Have I been? Has the Teams actually thing crashed? Maybe. I don't know. So I'll stop recording here.